Good morning, or good afternoon, depending upon your location. My name is Mary Hallisey, and I'm the Research Program Manager for the Wind Exchange Program at the National Renewable Energy Lab, NREL. And on behalf of NREL and the sponsor of today's events, the U.S. Department of Energy's Wind Energy Technologies Office, I want to welcome you to today's webinar. We're really excited to present an overview of offshore wind fixed bottom technology. Before we begin, I want to thank a few people, in particular our WEDO technical lead, Maggie Yancey, for her support with this effort, as well as the communications teams at both NREL and WEDO. And I want to thank you for joining us today. We have a great presenter, Walt Musial, who you'll hear more about in just a moment. And finally, I want to acknowledge NREL researcher and technical lead for this project, Liz Gill. Liz will be giving you a little bit of background about the webinar and some logistics associated with it. So once again, thank you. I think you'll enjoy the webinar today, and I'm going to hand it over to Liz.
Thanks, Mary. As Mary said, thank you so much for coming. And my name is Liz Gill. I'm the technical lead for the project. We're excited that you joined, and we're really excited that you're interested in offshore wind. I'm going to go over a quick few webinar logistics. So as you're aware, we're using Teams Live for this event. So through that platform, we'll be recording the webinar, and after the webinar, it will be posted to the NREL YouTube channel and to the Wind Exchange website. With the Teams Live platform, you actually don't have the ability to ask questions aloud, but there is a great question and answer feature to the right of your screen. And throughout the presentation, please feel free to post questions there, and we will be gathering those behind the scenes, and we'll be facilitating a question and answer section with our presenter, Walt. After the webinar, we actually will be following up with any questions we didn't get to and questions we did in written form to the attendees of this webinar. And now it is my pleasure to introduce our speaker, Walt Musial. So Walt is a principal engineer at NREL. He's the offshore wind energy research lead. And he actually started the wind energy research program at NREL in 2003. Currently, he chairs the American Clean Power Association's Standards Subcommittee and is a senior technical advisor for the National Offshore Wind R&D Consortium. Walt has a degree in mechanical engineering from the University of Massachusetts Amherst. He has 120 publications, 2 patents. Walt is the guy you want to talk to if you want to learn about offshore wind, and we're so excited to have him here with us today. So with that, I'm going to pass it off to Walt.
Liz, and thank you, Mary, for those introductions. That was great. Welcome everybody to this webinar. I'm going to give you an overview of fixed bottom offshore wind, and the reason why we added fixed bottom in there is because we're really relating this to the current technology, the status quo. I also want to thank the Department of Energy, the Wind Energy Technologies Office, for sponsoring this and putting this together. And this will be about we hope to end this in about an hour, but we'll leave some time at the end for Q&A that we'll receive through the chat feature that Liz just described. So I want to just jump right into this. This is a very new and exciting new field of energy. Offshore wind is a derivative of what maybe a lot of people are more familiar with, which is the land-based version of wind energy. But offshore wind is growing probably more rapidly than any other wind energy technology at this time. It's a zero carbon energy source that's available to parts of the country that couldn't traditionally benefit from large-scale wind development, because in coastal areas where there is a lot of resource for offshore wind, there's very little places to adapt that technology to land-based situations. And you can see from this map, which is a resource map, the darker bluer regions are the more energetic sites, and so there's more wind offshore, and there's more places to put wind farms. So the the highly populated areas of, say, the Northeast are going to benefit more, and then the West Coast, you see there's a lot of wind off the coast, and that is true for other regions as well. So the winds get stronger, they're more consistent, and larger scale projects are possible. Offshore wind, though, is really being a lot of the interest for offshore wind is coming from the other benefits that offshore wind creates in terms of economic development and the revitalization of our ports and our coastal communities that can benefit from these other opportunities for manufacturing and high-paying jobs. And I'll talk a little bit more about that as we get into this a little bit more, but a lot of it is being driven by the states themselves that see those other benefits. In accordance with a lot of that, we've now seen a lot of new support that's come from the federal side, and the White House made an announcement in March 2021 through the Biden administration that there would be a goal set for 30 gigawatts of offshore wind by 2030. That's in less than 10 years. We will have that amount of deployment of offshore wind. 30 gigawatts is 30,000 megawatts, if we're doing the units correctly here. And this is to advance the projects that are already well engaged in the pipeline, and to invest in the infrastructure that the U.S. needs for to advance that technology. So just having the technology itself isn't enough. We have to build ports, we have to build ships, we have to build factories to support this. And that and some of the research and technology that is still in development. This is technology such as floating wind, which will support deeper water installations or installations in areas like the Gulf of Mexico where hurricanes are prevalent, or in the Great Lakes where ice climates might limit the current technology. So there's new research that's necessary too, and that's part of this, the new coordination with the federal and the state side. And the picture on the right is a picture of a actual floating wind turbine that was taken in Scotland, and there's that was a site visit that we did. So another kind of milestone for the industry was Vineyard Wind 1, the first approved commercial project in the United States. It's an 800 megawatt project that's using this fixed bottom technology, and I'll explain more about what that is. They're using monopiles, and it's located 15 miles south of the island of Martha's Vineyard, which is off of Massachusetts in that map. And you can see the footprint drawn in the outline there, and the cable to shore is drawn in that yellow. It will connect in Hyannis and in that area, and provide power for approximately 400,000 Massachusetts homes. So this is a very significant project. It's one of 14 that's in the pipeline that have already submitted construction and operating plans to the Bureau of Ocean Energy Management, which is the regulator for all offshore wind projects in federal waters. The development of this project will result in what's expected to be about 3,600 full-time jobs over its lifespan. And it's using, notably, and we'll talk more about the turbines as well, the largest turbine available right now, which is a 13 megawatt GE Haliade turbine. And this allowed the project developers to really reduce the size and the footprint of this machine, or not the footprint, but the number of turbines being deployed at this, from down to 62 turbines, and it was originally at 108. So the larger turbines are being used by the developers, and that's a cost reduction measure. It's also the newest technology. So let's talk about the resource now. This map shows, it's another version of the first map that I showed of the United States. The resources, think of this as the fuel that's powering all of the wind energy in the ocean. And the darker colors relate to higher wind speeds. We look at the benefits of offshore wind, or the windiest sites, as the highest wind sites on an annual average wind speed basis. And the best sites are also in shallower waters. And notice the colors extend further out on the East Coast and in the Gulf of Mexico, and that's because we had a technology filter that eliminated all the sites that were greater than 1,000 meters in this map. So you can see from the map that the West Coast is very deep and probably won't be participating in the shallow water fixed bottom technology, but there's new technology that's being developed for deep water, and it will be deployed, we expect, in the next 5 years. And that will open up a whole new possibility for deployment. Deep water floating systems will be deployed, but I'm not going to talk about that in this presentation. I did a presentation last year, and I'll give you the URL for that to be able to look up the floating technologies session. But the key takeaway here is that the resource for offshore wind is about 2 times greater than the current projected U.S. energy use in 2021. So we have a lot of resource. Of course, we're not going to develop all of it, and we don't need to, but there's a compelling reason to look at what that resource can do for especially for the highly populated regions. So now I'm going to get into a quick description of just how a wind turbine works. And so this is kind of maybe a beginner section, because we have some people that really are, curious, because this technology has maybe become more part of the headlines, and people want to know how wind turbines work and how things are. And I think one of the things that people one of the first things they get wrong is the scale. These turbines are very large. One turbine can probably power about 4,500 homes in, say, the New York, Massachusetts area. These are big machines, and they're getting bigger. So the way they work, you see the arrow on the left. The wind is coming from left to right, and it impacts the rotor as it's moving through. And there are 3 blades on most wind turbine systems, and those blades can be controlled. They're mounted onto a turntable bearing, and they can be rotated to generate power, or they can be rotated to stop the machine. So as they rotate on those turntable bearings, you see the word pitch system. They can turn into the wind, we say, and then they start to generate power. And what they do is they generate torque in an upwind position. So the wind is passing through the rotor before it passes through the tower, and that starts to turn this giant rotor. That rotor on a GE machine is about over 9 acres in swept area. It's sweeping a circle about 9 acres big, and the wind passing through that circle if you weighed that air passing through the circle every 2 seconds, the weight of that air would weigh the same as this huge machine. So it's a lot of potential kinetic energy passing through this rotor at any given time. And what happens as this torque is created, it turns a generator that creates electricity, and that electricity is passed through cables down the tower and connected to a series of other turbines that are in an array. And that array sends the power to a substation, which is shown in the lower right, and that substation is connected to land, where a cable under the water is connected to substations and to the utility grid, where it's used by the communities and businesses and industries that inhabit the population. But in a lot of cases, these machines can be placed far enough out that you barely see them, or you don't see them at all. In this case, the machine has a direct drive generator, and that means that there's no gearbox, but some machines do have gearboxes. And the nacelle is something that is really a word that it encompasses the entire tower top, the part that's on top of this tower, and the tower is that tube that goes below it. The yaw system is a system that controls the direction that the rotor faces. And so there's a computer, there's completely autonomous, and there's a computer on board that determines which way the wind's coming from and is always facing this machine in the direction of that wind. And so that's kind of a simple but overview of the description of how the wind turbines work. The fixed bottom machines are very, very similar to the land-based machines. They were adapted from land-based technology, but now they are customized to work in the ocean. They're marinized. They have special corrosion protection and pressurized systems, different ways of keeping the salt water out. The substructures, which is the yellow piece that the tower is mounted to, that is a more complex substructure than the foundations for land-based machines, and they're designed for higher wind speeds. In general, most machines are designed to withstand about 150 mile-an-hour gusts, and so that's pretty high. But in some cases, we might even have to withstand higher than that in order to, say, resist hurricanes or large waves that are out there. The machines offshore, one of the biggest differences is that the machines are bigger offshore. The capacity is 2 times that of land-based turbines. I think probably more like 3 times in most cases. The average land-based machine in 2019 was about 2.5 megawatts, and this machine that you're looking at is 6 megawatts. I think the average offshore machine will grow quickly to above 10 megawatts in the next few years. So just a little bit more on how the wind turbines work. This is a picture of the Block Island turbines during one of the high seas days, taken by Dennis Schroeder. A power curve is the characteristics of how the turbine works. And we think of it in terms of 3 regions. Region 1 is when it's off and the winds are too low. That's typically pretty rare. It's more common that it's on. But then it starts into region 2, which is it follows a cubic function up until it reaches rated power. And when it reaches rated power, which is that dotted line that you see at 11 meters per second, it levels off, and this is where the pitch actuator system takes over, and it regulates power along that line in region 3, and it maintains the maximum power. It can't go over that because that's what the generator is rated for, and it stays at that level until there's just no longer enough wind for it to make sense to keep it online, and that's called cutout. A cutout happens at, in this case, it happens at 25 meters per second, which is kind of in the a little over 50 miles per hour, and then it just shuts down. And the way it shuts down is these blades feather. They call it feathering. The blades feathered, and the power. There's no longer any torque on the rotor, and the machine shuts down. And one of the reasons why wind turbines are so safe is that any one of the 3 blades can feather itself and stop the machine. So we have triple redundancy on all the machines that are out there, and that's an important safety feature that prevents machines from running away in the high winds. So one of the things that's most important to talk about in terms of fixed bottom technology is the water depth, and projects that are in less than 60 meters depth water use these fixed bottom foundations. That means there's a rigid connection between the turbine and the bottom. If you get past that point, and there hasn't been that much experience with this yet, but we don't see any technological reasons why we can't go in this direction, because floating systems, which you see the 3 on the right, will represent a great opportunity for new siting of wind turbines, but the technology is less mature. So today I'm going to focus only on the 2 turbines that shown on the left side, and there are other types of substructures besides the ones shown, but generally we're talking about fixed bottom systems, and that's where the majority of 99% of all installations so far have been fixed bottom installations. And so here are some other types and some of the ones that we've seen. We have the monopile, we have the gravity base, which is exactly as it sounds. It's just a massive piece of concrete, usually filled with rock, and it doesn't tip over because it's heavy. There's jackets that are more like sometimes they call them space frames, sometimes they call them trusses, and the jackets are another type. And then there's tripods, which have been used but aren't as common. 70% of the over 70% of the foundations so far have been monopiles. They get bigger, they've gotten deeper, but they haven't really gone past 60 meters yet. As we go to deeper water and different soil types, we're going to see that the different foundation types are necessary and not always the same ones. So this one, the monopile, is probably the most common. As I said, it's a pipe that, if you look at the center gray column, it's a pipe that's driven into the seabed. Typically 100 feet or more in. The diameters of this pipe are around, for the biggest machines now that they're being manufactured, about 11 meters in size. It looks like the monopile will remain the most common, for at least for the near term. It can be deployed in up to 50 meters, probably 60 meters in depth, but it's best used in stiff sandy soils. It's not very good in soft soils. It's not very good where there's boulders or rocks in the substrates that might cause the pounding of this pipe to be refused because it's hit something. It does require a very large installation vessel with a very large hammer, if you can imagine hammering in something that's 11 meters in diameter. And one of the issues that's arisen in this is the noise that's encountered during construction, which could disturb some of the marine mammals, and there's a lot of precautions that are taken in that regard to make sure that we do not harm any marine mammals in doing that. But it does create barriers in weather windows and when the construction can take place. The next type that we would have in our toolbox is the gravity-based foundation. There's multiple types that can be used, and they're generally made out of concrete and maybe more adaptable in some cases to the local manufacturing. They're ballasted after they're put in place in the seabed, and extremely durable. They could last a long time, maybe even longer than the turbine. And the installation considerations that we look at are, can they be installed in soft soils? And in some cases, you have to be really careful, because if it's too soft, they'll settle and they won't stay level, and that would be a major problem. So there's a lot of cost uncertainty about how much seabed preparation needs to take place. But in some cases where you can't drive deep piles, this might be the best option. In jackets, these are very common in the U.S. oil and gas industry, and they've taught us a lot about how to make these jackets. They can be attached. They also need deep pile driving, but the piles are much smaller, so they lend themselves in some ways to, they may be more suitable in some conditions. They also might be cheaper, but they can also be fabricated in U.S. factories that already exist. So whereas there's one monopile factory being developed right now, so we'll see how the supply chains develop, but a lot of the choices may become mostly dependent on where they can fabricate them and how much they cost. Tripods are another option, generally very close to the jacket, except they have a much lower profile at the water surface, which could be an advantage in some conditions, especially say if there was ice on the surface and you didn't want ice jamming in a jacket, or and you didn't have the option to do a monopile. But this is another variation with deep piles, and we saw some of these in the very first German project, for example, Alpha Ventus, that use tripods. Scour is an issue that comes up a lot in fixed bottom systems. And this scour is something that happens at the base of a turbine or a base of a foundation or a substructure, especially with monopiles. If you have currents that are moving past the base, you can get swirl and turbulence around the base, and it can take away the sandy soils that hold the foundation in place. And that movement of the seabed can alter the design conditions substantially and compromise the design. So you need to have a material like a riprap or a rock that's put down around those bases so that the scour doesn't occur. And that's it's a pretty simple concept. These scour can be put in place by these ships that drop it down there, and it's pretty effective in keeping those sands from eroding and compromising the depth of penetration. A substation is part of the electrical supply, electrical system, the infrastructure, and almost all utility scale wind farms are going to have a substation. And by a utility scale, I'm talking about hundreds of megawatts. And we need to build utility scale systems because that's where we achieve the cost benefits of large scale economics. So a small project like Block Island is not going to be competitive on the energy markets because it's too small. When you get up to the Vineyard Wind scale, 800 megawatts, now we're talking about cost-effective projects that can be put in place and that can compete on the energy markets, but you need these substations in order to do that. These are connected at high voltage to the land-based grid, and high voltage is at a minimum of 115 kilovolts, but they can be more, and these export cables carry the power from the substation to the land-based substations. And so all of the turbines on their array strings are connected to this. Here's just a quick photo of the Alpha Ventus. This is the German project, and it's a combination of these jackets, which are you've seen in the truss projects, in the tripod, which is the one that's closest. And the tripod looks like a monopile, but it's not. It's got 3 legs underneath the water surface that you can't see. So now I'm going to just pan back a little bit and look at the global situation for offshore wind. As I said, 99% of offshore wind farms have fixed bottom foundations, and that's the status quo technology. As of the end of December 31st, 2020, there were 32,906 megawatts of offshore wind capacity installed worldwide. Only 82 of that is floating. And if we focus on the United States, we're hoping to join that group that's deploying that. It's about what the U.S. plans to install in the next 10 years. And if you want my sources, this is the market report that we publish every year with DOE, and it's down there. And this is a chart that's taken from that. So it shows the bottom, the annual additions, and then the cumulative additions on the top. And it's a growing industry that keeps growing. So I'm going to click through some of this here. This is where in the United States we're looking at fixed bottom systems. We have the North Atlantic, where we have most of the activity right now, the Mid-Atlantic and South Atlantic. These are all areas where there's already been leasing activity. But we also have the Great Lakes. The Great Lakes has a significant amount of shallow and deep water. It's not under the same jurisdiction, though. These will be state jurisdictions, and will have to and won't be going through the Bureau of Ocean Energy Management as its regulator. In the Gulf of Mexico, we'll see the same kind of activity as in the Atlantic, but it's a little more delayed because the markets might be slower because the winds are lower, and there's still some technology issues with developing robust systems to withstand hurricanes and low wind speeds. Won't talk about that on this one, but if on the Pacific coast and in Hawaii, we're talking about new technology for floating systems. Here's a chart that's really showing the process of regulation as a project goes through, and not all of this is controlled by the developer themselves. This is really the Bureau of Ocean Energy Management's chart, and it's complicated, so I won't describe every aspect of this, but it's really important to see at the blue middle part, there's a label called lease granted. In order to build a project, you have to have a lease, and a developer cannot build one without one. So that's a key step. So once a lease has been granted, and that means purchased really by the developer, then a lot of this proprietary leasing activity can go on, and that can take several years. Some of these numbers are in years. The BOEM is working to shorten this as much as they can, but there's a lot of things that you can't avoid. There's pre-survey assessments and physical and environmental that have to go on. But the developer eventually submits a construction and operating plan, which it goes into the review at BOEM, and then that plan gets approved, which is where Vineyard Wind now is, and that's out toward the red side, at which point they can start construction and finalize their financing, and then install the turbines and then operate the turbines. That operation can go on for 25, 30 years afterwards. So there are 14 projects, big projects that have submitted construction and operating plans, and one has been approved. And so we see that as also the flagship for the other 13 that will be coming through. Here's a chart that shows the activity in terms of land area and leases. The lease areas, the ones that where developers have site control are shown in kind of this rust orange. The lighter kind of yellowish mustard color are the call areas. Call areas are precursors to wind energy areas, which can get which turn into lease areas. So the call areas are still under investigation, and to see if the Bureau of Ocean Energy Management submits calls for nominations to see what kind of competitive interest there is in various areas, and then as the stakeholders weigh in, they turn them into wind energy areas, which are typically smaller than the lease areas, or than the call areas, sorry. And you see that there's half the call areas are on the West Coast. They haven't developed any lease areas yet on the West Coast. And on the East Coast, it's a combination of unsolicited or unleased wind energy areas and lease areas, where there's 16 now lease areas, totaling a potential technical capacity of about 11,652 megawatts, which developers already have rights to. And then there's about 12,000 megawatts of capacity that haven't been leased yet. And so there's been some notices recently that suggest that those leases may go forward soon. So switching now just to how do these projects go in? How are they installed? We need big ships, and if it's not obvious, look at some of these ships and look for some of the features that would indicate how big they are. But they are massive. These are called jack-up barges, and they have very high lift capacity cranes that can install the machines in place. And you can see for fixed bottom systems, these jackups are touching the bottom. They have legs that go all the way to the seabed. For floating systems, you can't do that, and there'll be a different strategy for doing that. So this is a good way of seeing how the installation happens. When we're doing operation and repairs, they can do it with smaller boats and ships. There's an example of one in the Baltic where it's a fairly small ship that was docking at the ladder, and then the personnel can just hop right off if the seas are low enough. For major repairs, they still need to bring a crane out and lift the components out. A lot of the designs now are focusing on trying to do those repairs in situ because it's expensive to bring the crane out. So turbine spacing is a big issue, and one often asks how do we determine how far apart to put the turbines? And it's really a non-dimensional decision. It depends on the diameter of the rotor. So as the diameters increase, the spacing increases, and it's not a fixed distance. What's important to note is that the turbines have to be far enough apart because each turbine is taking about half of the kinetic energy out of the wind, and it needs to leave some for the downstream turbines. That's kind of a theoretical maximum. 59% is the actual theory of how much it can extract. But if it's important that energy gets replenished, and the way it gets replenished is that the wind, as it's moving downstream, mixes with the wind above, and it replenishes the free stream wind in front of the next row of turbines, and leaves some for the next turbine to get. But there are losses, and those are called wake losses. So we try to space these rotors far enough apart. For a GE 12 megawatt turbine, 8 rotor diameter spacing is not out of the question, and that's about a mile apart between turbines, and that leaves a lot of space in between for the wind to regenerate itself. It also leaves space for navigation and for fishing vessels to possibly fish in between the turbines, possibly trawl on the bottom, and to make wide turns and navigate through, especially in inclement weather where the turbines may become either a barrier or an obstacle, or may become a navigation aid. And I think there's a very strong interest to coexist with the fishing community in these situations. So we're still working on that, and rotor spacing is kind of a key issue. Here's one example: is if you put the spacing too far apart, then there's a higher cost associated with that because you have to purchase more array cable and connect them, and the site has less impact. It can't generate as much electricity. So there's an optimum between how far apart the turbines are spaced and how much array cable you need in order to generate the power and send it to the substation. So this is kind of a schematic of, if the turbines are the dots, the cables connect the turbines to each other and strings, and then those strings are aggregated and brought to the substation, and then one export cable will be brought to shore. If it's a big project, it might be 2 or 3 export cables, depending on the size of the project. And those voltages at the array are lower than the voltages that the export cable carries. The export, so that's what one of the functions of the substation is, to increase that voltage. Currently, array voltages most projects were built at 33 kilovolt, 33,000 volts between the array cables, but almost all the projects are moving now to 66,000 kilovolt or 66,000 volts, and that helps. With the spacing, it helps connect larger turbines, and it helps lower the cost because you need less copper as the voltage goes up. The other thing we need as we build these projects is our ports and port infrastructure. And you might not know this, but there are really no ports that were completely set up for offshore wind. A lot of the ports that exist have to be modified, and maybe some new ports have to be built. But in the process of doing this, it creates great opportunities for commerce in the offshore coastal communities. But every port needs a wharf space to be able to dock a ship and have bearing loads to offload these very, very heavy components, 600 tons at a time, onto the the quayside. They need a navigation channel to be able to bring the large turbine installation vessels in and out, equipped with all the components that are necessary. And these ships have to be flagged with U.S. flags if they're going to deliver goods from the port to the wind turbine site itself. So that's called the Jones Act, and that's something that's actually stimulating the shipbuilding industry in the U.S. The upland yard is where we store the components, and we need large acreage for these very long blades. The blades are the length of a football field, and there's for Vineyard Wind, there's 62 turbines. There's almost just a little less than 200 of these blades, and they're each a football field long. So we need a lot of space. We need cranes that can lift and do some of the assembly. The requirements for cranes for fixed bottom systems are lower than they are for floating systems, because the assembly mostly takes place at sea, but we still need to make sure that we're adequate. And then the crew access and maintenance vessels have to have a place to go as well, and that's part of the whole infrastructure port requirement. So how much does I'm going to move to cost real quick here and talk about how it breaks down. A lot of people look at an installation and see the turbine and think that that's the whole thing, but it's actually only about a quarter of the cost of the whole system. The what we call the balance of plant or the balance of station makes up more of the offshore wind cost, and that includes the project management, engineering, and the substructure and foundation design. A lot of that mobilization of the marine equipment that has to go into this, the electrical infrastructure that I've described, and the insurance and decommissioning costs that get packed into this, that makes up the lion's share of this. And it's also where most of the local jobs come from. The turbines, so the turbine is not the most important part, believe it or not. And the last piece of that is the operation and maintenance, and this is something we can control a little bit as we get more mature to be able to lower the slice and how much it costs to keep the turbines running over, say, a 25 to 30 year lifetime. And costs are coming down. This is a chart that shows the final strike prices of a whole bunch of projects that have been recently bid in Europe, and some of the US projects that go with them. And we've seen over the last 5 years a 70% decrease in cost over these projects. And the reason why they're coming down, we've seen the introduction of bespoke or custom offshore wind turbines that are getting larger, and so the technology is getting better. The risks are lowering because the supply chains are maturing and growing, and so there's a lot more certainty about how we're going to deliver the products and assemble everything. And then there's increased competition that has come from a lot of players getting involved in this and bidding the projects down in these areas. And we've adjusted these strike prices to include everything that a US project includes, not some of the, say, German projects only have to connect to substations out at sea, but we've adjusted for those costs in this, because in the US, the project accounts for everything, all of the costs, including the connection to the onshore grid. So now I just want to kind of, the last stretch here is to finish up and talk about how big will these machines get. We've seen the turbines in Block Island were 6 megawatts, but every major OEM original equipment manufacturer, turbine manufacturer, has introduced at least a 12 to 15 megawatt turbine, at least in the prototype stage by now. And so the turbine size has doubled since the Block Island machines, and we see that growth is likely to be introduced commercially, certainly by 2030. And there's also some talk that those turbines could grow up to even beyond that. There's a 17 megawatt turbine that's been described, and that may continue. That trend may continue. The development of the infrastructure is something that has to be weighed against the turbine growth, because each time the turbines get larger, the infrastructure has to get larger to go with it. And so the industry will have to make a decision about whether it wants to continue to make larger turbines or whether it wants to stay at one level and industrialize the process of being at a big enough size that it can benefit from the scale, that the costs at that scale. So, but in general, larger turbines are cheaper because there are fewer installations that need to happen. There's fewer trips to the turbines, and transportation constraints are not a big issue, not as big as they are on land, at least. And so they have lower project costs and lower maintenance costs. And again, we don't see any hard limits to further turbine growth, but there may be some economic benefits to either staying where we are or continuing to grow larger. And when we shift to floating, it's really not going to change much because floating systems are using the same turbines as fixed bottom systems. So this graphic is really just showing the scale of the reference turbine that we developed, and it's a reference 15 megawatt machine that is 240 meters in diameter. It's very close to the Vestas machine that was just announced, which is 236 meter rotor, and that will be available according to Vestas in 2024. And here are the bullets just describe the size of the three major turbines that have been introduced. The chart on the left shows the growth in size. The bars are the nameplate capacity, and the curve above that are the prototype sizes that were deployed in the same year that we averaged those nameplate capacities. And you can see that the turbine prototypes are continuing to exceed the average size of turbines being deployed, and will continue to do that for some time. But we'll see these bars level out or continue to increase as these prototypes get introduced. And there's a picture on the right of the GE turbine being the first prototype being rolled out in, I believe it's in France. It's a big, that's gives you a very good indication of the size of the nacelle of the 12 megawatt machine. So just quickly talking about economic impacts, the Biden administration estimates that if the 2030 30 gigawatt goal is met, that we'll have an estimated 77,000 full-time equivalent jobs that will stem from this. And some of those come directly from working on the project itself, but there's also just economic activity and indirect jobs that get stimulated in the communities that support these projects, and that also represents growth. But at face value, this status quo of this industry is looking like it's about a $12 billion per year capital investment for the U.S. and for the U.S. economy. And so I want to just finish up and talk about my takeaways. You've seen that offshore wind energy resources are close to the population centers, and that's enabling the coastal states that are highly populated to take advantage of this new carbon-free energy source that's proliferating rapidly. About 99% of those installations are these fixed bottom foundations, which we see in Europe, and we see a big market happening in Asia as well, and that will soon come to the US. The costs and what's probably stimulated a lot of interest from the states is that these costs have come down by approximately 70% over the last 5 years, and now have, at least you can see the light that these may be able to compete in some electricity markets without subsidies. And certainly that's true in Europe, where they're already bidding these projects without subsidies. In the US, we may not be quite there yet, but the states are providing the differences so far, and those differences are getting smaller as the costs come further down. Larger turbines are leading the way for a lot of the cost reductions, and we've seen that, and we'll continue to see as these new this new wave of new larger turbines come online. We'll see those costs realized, and then keep our eyes out for floating wind, which is something that's going to enable the West Coast to engage in this. And it also will expand the options for siting on the East Coast too. So I'm going to stop there, and I have one last slide just to finish with the Block Island slide, which is also the slide that's behind me, and I'll take some questions now. So I'll turn it back over to Liz.
Thanks, Walt. That was a great presentation. We all really appreciate your time, and I think we all learned a lot, including myself. So a lot of questions came through over the chat, so we can dive right in and take about 9 minutes to go through some of them. So we talked a lot about the cost of offshore wind, but can you talk about the cost of offshore wind in comparison to land-based and what the difference is?
Yeah, I don't have the exact numbers for land-based, but the land-based wind is the cheapest form of energy on the grid in places where they're building it now, and we've seen land-based wind prices as low as $30 a megawatt hour or lower. So the biggest challenge for land-based is transmission, and it's certainly not cost. It's cheaper than natural gas. It's as cheap as solar in areas where solar is being built. So it's offshore wind. Our targets are somewhere around $50 per megawatt hour. Sorry, per megawatt hour. The costs on some of the projects are approaching that right now, and we think that we can compete at that level in the coastal communities where the energy prices are much higher than they are in areas where land-based wind is being built. So the economics really depend on what the current costs of electricity are, what the competing costs of electricity are.
Great, thanks. Can you talk about advantages between concrete foundations over steel foundations? Like what are some of the considerations? And then with that, what are the substrate considerations? Where is most of the siting of offshore wind happening in relationship to what type of substrate is on the ocean floor?
Sure, I don't have detailed information about the substrates. I know that there are some sites that are rocky or have glacial moraine where monopiles or pile driving may be difficult or impossible. There's also areas where the bedrock is close to the surface, maybe in Maine or in the Great Lakes, where pile driving may not be possible, deep pile driving. So we may need to see gravity base, but gravity base or concrete is not limited just to gravity base. There's other types of foundations that are looking at concrete right now, and there's some big advantages to concrete because concrete, first of all, it doesn't rust. Or it can be designed for much higher lives. We see that in the bridge building industry. The University of Maine is developing a concrete floating system, but there's also concrete gravity base. One of the big advantages of concrete is that it lends itself very well to local production, where complex steel structures need different types and more complicated factories, larger investments to make those factories happen. Concrete factories are thought to be easier to implement, and so there may be an advantage to local labor in building and using concrete as the primary material for some of the substructures that we're looking at. Gravity base. There are some prototypes looking at fixed bottom systems that use concrete as well.
Great, and you had mentioned the Great Lakes, and we had some questions come in about what are the factors limiting development in the Great Lakes? Are there factors limiting the Great Lakes? What do you see as the prospect for development there?
Yeah, it's a pretty early stage. The big question we always get is, won't ice knock the machines down? And we think right now that the ice can be engineered around. And the question that we're trying to answer right now is, can floating structures work in the Great Lakes? There's a lot of resource in deeper waters, and of course, the residents and the stakeholders of the Great Lakes would like to have the option to move projects further from shore, which is deeper water. So that's a consideration. The Great Lakes soils tend to be silted, and the bedrock is pretty shallow, so there may be a need to look at foundation types that have a different orientation than the Atlantic. But I'd say it's we're not ready to make any conclusions on that yet. Hopefully that helps. Lake Erie has a project called LEEDCO, called Icebreaker, run by a company that was started for the development of offshore wind in the Great Lakes, called LEEDCO, and they are proposing a 21 megawatt project off the coast of Cleveland, which would be the first offshore wind project, fixed bottom offshore wind project in the Great Lakes.
Great, thank you. We've had a couple of questions come in about the lifetime of an offshore wind turbine, and especially for fixed bottom. Can you speak to how long we're expecting them to be able to last?
It's a very good question, and it's a dynamic question. The early projects, not just offshore wind, but the wind industry, had a design life of 20 years, which was a very conservative lifespan. As the industry matured and aged, we realized, because a lot of machines were still running after 20 years and could continue to run, that maybe those life extensions should be, the life should be extended. So the industry is moving more toward 25 years. And I always say, well, it could be 25, it could be 30. It depends on the design of the project, and it's usually dependent on the turbine life. I think the components in the turbine, because there's a lot of cycles on the blade and on the gears and on the generators, that those components will wear out faster than the foundations that are static. But it's yet to be seen what the actual life will be. But I think there's a movement toward a longer life. It's just because it makes sense.
So just as a follow-up to that, we've also had a couple questions about, when those turbines reach end of life, what is the industry looking at for decommissioning plans? Do they know what that will look like? How much of the turbine will be left in the ocean or not?
Yeah, I don't think that's been that's a decision. Life extension, end of life management will probably be done on a case-by-case basis based on economic factors. I don't think it's going to be a one-size-fits-all, but there is a requirement that the developer consider the cost of decommissioning at the time that the project is permitted, and there's a surety bond that BOEM collects that will ensure that there'll be some funds remaining in order to pay for decommissioning if that's necessary. But there's also repowering, which means that they take the same site and they put new turbines on, or they retrofit turbines, which could be just take the same turbines and upgrade them, fix all the parts that are worn out, and keep going. So those decisions have to be made, I think, on a case-by-case basis, and we're far from having to make those, as the industry only has 7 turbines in the water so far.
Absolutely. Well, we are just about to hit noon, and I want to make sure that everybody can get off and get to whatever they're doing next. But just want to thank you, Walt, so much for doing this presentation. We really appreciate it. I wanted to answer a few questions that came up in the chat that were more logistical. So we will be publishing the slide deck and can follow up with everyone attending here once we get that through our publication process. It will also be posted to the Wind Exchange website. So we'll follow up with all that information, as well as the link to the floating offshore webinar, which was asked for a couple times in the questions as well. So with that, please feel free to follow up with me if you have any questions, and I think we're ready to sign off. So thank you everyone for attending.